Action.
I'm gonna have a stroke.
All right, kids. So let's chit chat about this concept of net forces. So we're actually going to start like a trifecta of like 3 labs in a row. To kind of show how this deal works. So that's what I found most effective was like, can you really see how this plays out? So here's your basic idea. On every one of these problems, start with this idea that force net is going to equal the sum of 2 forces. Force applied plus force opposed, okay? And it is only, and I emphasize this again, it is only in any situation the net force that equals mass times acceleration. Okay, that's it. Now, that net force might be gravity, that net force might be friction, that net force might be the applied force. There's a whole bunch of different manifestations of that net force, okay? But at the end of the day, the net force is kind of like the summative total of what's happening. So if you look on that first column, okay, so here's this truck, right? And it's moving along, right? And it's going in this direction, okay? You want to stop the truck. You want the truck to accelerate, right? That's it. So the only way that truck is going to accelerate is if there is an imbalanced force. So if you've got gravity acting on it and the normal force acting on it, okay, well, neither one of those are going to make the truck accelerate because those forces are all balanced out. What are you doing? Okay, I look up here doing hand-to-hand combat with macrame. It's for what? Okay. Would have never guessed speech. What class?
What is the speech about?
I have to give a demonstration about how to make a friendship bracelet. So.
Gotcha.
Yeah.
Gotcha. Because I just look up attack by thread. Okay. So back to our story of net forces. So after my ADD kicked in for just a second. So here's the deal. Kind of. So in this situation, your FG and your force normal are not going to be the imbalanced forces, okay? Because they're sitting there on the road, gravity is pulling it down, the normal force is pushing it up. So the only way that this truck is going to accelerate, and this is true every time you all drive your car and you hit the brakes. You hit the brakes to accelerate. You hit the brakes to change the velocity vector. Okay, that's it. So you're driving along, oh, gotta stop, boom, hit the brakes. You're going to accelerate. That's going to happen because there's a frictional force. So that frictional force is always in the opposite direction of motion. Okay, no exceptions. Forced friction always acts in the opposite direction of motion. So right away you sit there and go, okay, hey, I've got a positive velocity. I'm going to slow down. I have to have a negative acceleration, which means I have to have a negative net force. So when in doubt, set up a chart and go, okay, force applied, force opposing, force net. Okay? So there is no applied force to this truck. We're not like pressing down on the gas pedal and hitting the brakes at the same time. Okay? There's nothing there. So the only thing, there's no applied force. So the only thing that's going to make this truck stop is the opposing force. And then you ask me, what's the opposing force? You got one of 2 options. Your opposing force is either gravity, so it's the gravity mafia or the frictional mafia. That's it. Pick your mafia. So in this case, what's going to stop it? Frictional mafia. Because gravity mafia is being bounced out by the normal mafia. Oh, okay. So now I have to find my net force. So if I find my net force, right away I know what my frictional force is because that's what's going to make the truck stop. And the next question is, how do we find the net force? Well, net force and only net force equals mass times acceleration. Then you go, how? How do I find the acceleration? Conveniently, you have an initial velocity, a final velocity, and a distance, which leads, we can use that equation. So if you use that equation, you should get an acceleration, this is an ish, around -8 meters per second squared. Okay? So that's about what your acceleration should be. Okay? then you can sit there and go, oh, force equals mass times acceleration. So you have the mass. Do not take that mass and multiply it by 9.8 meters per second squared to get the weight. That's not what we need. We need the mass of the truck, okay? Not the weight of the truck, we need the mass of the truck. So just take those kilograms straight up, multiply it by that acceleration, you should get something times 10 to the fifth, okay? It's a pretty big force, but you're also stopping a pretty big truck, okay? So that answer on number 1 should be negative number, something times 10 to the fifth, okay? Now, on 2, you're going to find the coefficient of friction. And I know there has to be a coefficient of friction, because if there wasn't any friction, the truck wouldn't stop, the truck would keep going along in a straight line, like I showed you yesterday with the little hovercraft, okay? When I hit that hovercraft thing, it didn't stop because there wasn't any friction. So, we did that. So, there's a couple of ways on number 2 you can calculate mu. You can use force friction over force normal, and your force friction is what you just found as your answer to number 1, okay? Because that net force is your frictional force, okay? So you already have the top number, okay? You don't need to do anything. It's there. You have the top number. That's your answer from number 1, because that's what's making the truck stop. Now, the normal force is the same as your gravitational force, which is mg. You have the mass of the truck, you know what g is, multiply those two numbers together, you're going to have that answer from number 1 divided by the weight of the truck, divide them out, it's an absolute value, okay, mu is never negative, and so if you do it that way, you should get a mu around 0.8, okay? So that's kind of the long way to do it. So if you're into forces, you're going to work in. I always wanted to be like this Jedi thing with the force was with me. I always like to work in forces. Cool, okay? Jedi Master, there you go. There's a ratio of forces. Now, if you like a simplified version, you could sit there and go, well, my force friction is the same thing as my mass times acceleration. Come on, okay? So we can rewrite this, I'm out of electrons, as mass times acceleration over mg. So the masses actually cancel out. So the shortcut way to do number 2 is that you take that acceleration that you found up there at number 1, you divide that by 9.8 meters per second squared, you're going to get the same answer, it's just a little bit less complicated, okay? So you can either take the ratios of the accelerations, or you can take the ratio of the forces. You're going to get the same answer either way. So your answer to number 2 should be around 0.8. What are the 2 most important words on number 3? Constant velocity. All the forces add up to? 0. So you have no net force. So here's what's different on number 3. So make this chart. You have force applied, force opposing, net force. What do you want the net force to equal? 0. So you're told that it takes 16.4 newtons of force. That's your applied force. So what does your frictional force have to be? Negative 16.4. Okay? So there's your force opposing, which is your frictional force. That's what you have to pay off to the frictional mafia. Then you want to find mu. Oh, that's force friction over force normal. That force friction is your 16.4. Find the weight of the chair. There you go. So your answer to number 3 should be around 0.3. Okay? It's an ish, but something around 0.3. Number 4 is the easiest problem on the entire assignment. All you have to do is say, oh, I have a net force of 18 newtons. It's acting on a 1.5 kilogram box. Take 18 newtons and divide it by 1.5 kilograms. You get an acceleration. Okay, that's it. All you have to do. Do not make number 4 difficult. Now, if you look at what happens on a difference between 4 and 5. On 5, we're still applying the same 18 Newton force. So my force applied is still the same. But because I've given you the coefficient of friction, now you have to figure out, now you have to use that information to figure out how much do I pay the frictional mafia. Okay, so the frictional mafia is going, hey, we got a coefficient of friction of 0.540. You have to calculate that force friction. So if you do that, in round numbers on number 5, that force friction should be around 8 newtons. Okay? So here's the setup. So here's this box. You're applying a horizontal force of 18 newtons. And round numbers, you have an opposing force of negative 8 newtons. Okay? So you're pushing with 18. The frictional mafia is demanding that you pay them about $8. What do you have left over? About 10 newtons, right? You have about $10 left over. After you pay the frictional mafia, it's the cost of doing business, okay? That leaves you about 10 newtons left over. That's what's left over to accelerate the box. So what you should see, and hopefully this makes sense, and just intuitively it should make sense. Oh, there's friction. Yeah, right. If I apply the same force and there's friction, I should get a smaller acceleration because I've got to take some of that force that's going to get used up in overcoming that frictional force. Okay? So what you should see is that your acceleration on number 8 should be around 7 meters per second squared. Okay? So your acceleration is less because you had to take some of that force and use it to pay off the frictional mafia. Okay? Cool with that one? Got it. Okay. Now, on the diagrams, you should have something that looks like this, and this is drawn like with a ruler, with a scale. So you should have something like this: a gravitational force, a normal force, a force applied, a force opposing. Okay? And then you should draw that tip to tail, FG, force applied, force normal, force friction, and you should end up with a gap. That gap is your net force. Make sure you draw in that result, because that's fundamentally what's going to make this thing accelerate. Okay? Cool with that? Kids, I'll be okay.
No, I have my results in.
All right. Now, here's the other, and this is what the lab that you're going to start today. And this is dealing with the rocket. So, any rocket, if it's going to get off the ground, your force applied has to be greater than the weight of the rocket. So here's the analogy, okay? So Taylor goes down to the gym, and Taylor's going to lift 500 pounds. Okay? 500 pounds. Now, if Taylor only lifts up with a force of 499 pounds, Taylor, are you going to be able to lift that set of weights?
No.
No. She's going to try. Veins going to be popping. Oh, right? If she can only lift 499 pounds, which is impressive, she's not going to budge the 500. Okay? Now, but what if she can just apply 501 pounds? If she can apply 501 pounds, will she be able to lift the weights?
Yes.
Yes. So, if you look at a rocket, it's the same idea. The engines from the rocket just have to apply enough force to overcome the gravity mafia. Okay? That's it. So as long as that applied force is bigger than the weight of the rocket, you're going to get a positive net force, and the rocket's going to accelerate upward. So what's happening on number 10, here's the rocket. You got 129 Newton force. is that my applied force, my net force, and my opposing force? That's your force applied. So then you gotta ask yourself, what do I have to pay the gravity mafia? I don't know. We can figure that out. You know the mass of the rocket is 5 kilograms. Multiply that by g. There's the weight of the rocket. So you've got 129 Newton force acting up. You've got the gravitational mafia pulling down, and the difference between them is your net force. That's what's actually left over to accelerate the rocket. So on that diagram, this is all I want, something like this. Okay, you don't even have to draw a cool rocket if you don't want to. But here's the whole idea. Your applied force, you have a certain amount of gravitational force, hopefully you have a positive net force, that's going to get the rocket off the ground. So all I want on the velocity diagrams, come in here and go something like this. Here's V1. Hopefully your second velocity vector is bigger than the first one. That's the whole point of the engine. And then because your velocity vectors are getting bigger pointing up, what's the direction of your acceleration vector? Oh, don't make this difficult. Draw an acceleration vector pointing up. That's all you have to have. Okay? These are just sketches. They don't have to be to scale. All you're trying to convey to me is that I understand that, oh, when this happens, my velocity vectors are going to be getting bigger. I'm going to have a positive acceleration vector. Okay? That's all you have to have. So, your answer to 10D at the end of 12.6 seconds should be around 200 meters per second. Okay? Which is about 2/3 the speed of sound. Okay? You're hauling the mail. Okay? Pretty good for that. All right? Now, at that point, we're going to shut off the rocket engines. Okay? So, as soon as you shut off the rocket engines, that's analogous to me throwing this apple up in the air. As soon as, and this apple weighs exactly 1 Newton, it even says 1 Newton, okay? So as soon as that apple leaves my hand, what's the only force acting on the apple? Gravity. Now, if I want to throw the apple up in the air, does the force that I apply have to be bigger or smaller than 1 Newton?
Bigger.
Bigger, right? Because if I don't apply a force bigger than 1 Newton, it really doesn't go anywhere. But if I apply a force bigger than 1 Newton, it accelerates upward. But as soon as it leaves my hand, the only force acting on it is gravity. And guess what? What does it start to do?
Accelerate.
To accelerate.
Okay, well,
And that acceleration is going to make it
slow down.
So what I'm looking for on E, okay? You should have 2 distinct sets of diagrams. What's happening on the way up, and then what's happening on the way down. So this is right before it hits its maximum height, and right after it begins to fall. Okay, so listen to me. The engines are off. There is no applied force. Don't draw an up arrow, okay, for a force applied. There is no force applied. I let go of this thing. The only force acting on it is
Gravity.
Do not confuse inertia with force, okay? Does the apple want to continue to go up because it has inertia? Yes, okay? But inertia is not a force. Eli.
Okay, so when you want 2 sets of sketches, right?
I
But
do.
is the free body diagram any different on the second one?
No.
Or you just want 2 of the exact same sketch?
Yeah.
Okay.
All you have to
Wait,
do is
what?
draw- all
You
do
have
is-
the same
all you have to
sketch.
do is
You're
draw
good.
down an arrow that
You're
says
good.
FG.
You're good.
Okay.
You're good.
It's the easiest point you will ever
You're
get in
fine.
this
You
class.
have exactly what he said. You're good. Don't stress. She's stressed because she's the same graph, and then she says she doesn't have the same graph, but it's the same graph.
Here you go.
No, you said they're supposed to be the exact same.
No, just in terms of force.
Well, no, I know. She has that, but she was
Is it
freaking
okay
out
if
like
it's
she
on the
doesn't
same
have
free
that.
body like this? I worked really hard on this too.
She drew her rocket upside down.
Yeah, I drew it upside down when it starts to fall.
That's not accurate.
Maybe it flips over.
Does this count?
No, it doesn't flip over.
Yes, it will.
How do you know?
Rockets don't land tipped first.
Okay, well, this is where it's beginning to fall.
Yeah. It's still going up when its engine stops.
So this is on the way up, this is on the way down.
Yeah, it begins to fall. I labeled it.
Okay. You're okay.
Okay.
Yeah, that's what I said. No need to stress,
I
Morella.
don't know, the way he was looking at it just now, he was
Well, I
like,
had to figure out, usually it's like on the way up and on the way down, and you labeled an engine off, so that's what I had to,
Hey,
oh.
that's what I was
It's
trying
okay.
to sort
No.
out.
Please change your tip.
Okay,
I want to trust me.
on the velocity time graph, your velocity time graph should look something like this, right?
Oh,
Keep a running clock. You have 12.6 seconds. That's while the engine is being fired. Now, think this through. This is a logic problem. What does the slope of a velocity time graph give you?
acceleration.
Acceleration. How do you use acceleration to calculate net force? Mass times your acceleration gets you your net force.
C.
So if you change your net force, you change your acceleration. If you change your acceleration, you change the slope of your velocity time graph. So anytime you see a change in the slope, not necessarily changing the sign, even if you see a velocity time graph that goes something like this, okay? Every time the value of that slope changes, that means you're changing the acceleration. The only way you can change the acceleration is if you change the net force. Okay? Now, if this is a rocket, the only way you can change your net force is by changing your applied force. So if you change your applied force on a rocket, you change your net force. You change the net force, you change the acceleration, therefore you change the slope of your velocity time graph. Okay? So it's like this cascade of logic. You do this, that causes a change in this, that causes a change in that. Okay, so make sure on H that you have a whole bunch of things labeled. I should clearly see the acceleration on each side, the net force on each side, when the engine is shut off, when the rocket is at its maximum height. Okay? So if you're not sure you have those, give your paper to the person next to you and go, hey, can you see what I've done? And if they go, then no. Okay. Now, on 12, let me give you all a hint on number 12. So I say, explain in terms of opposing force, net force, and acceleration. What three words do you think you ought to mention when you answer number 12? Net force, opposing force, and acceleration. Okay, if you have not mentioned those, that's bad. Okay, that's bad. And if you haven't mentioned like the word acceleration, just don't write the word acceleration at the end. Okay. Are we good? Anything else? Once?
No, sir.
Twice? So make that happen. So,
What?
okay. So what we're going to talk about now is, this is oddly enough, just this manifestation of this idea of net force. So this is the Saturn V rocket, and that's the rocket that got the astronauts to the moon on the Apollo missions. So if you look at this whole idea of net force and force opposing. So this rocket is very massive, okay? And we'll start to show this in just a second. So we'll roll this for just a little bit here.
Billowing clouds exhaust, and in blinding pillar of fire, a mighty voyager behind to explore the vast.
Okay, so let's talk about the mechanics of how these engines work. So here's the unique engineering challenge of these rocket engines. So first off, if this thing is going to get off the ground, your engines have to, like we talked about, have to provide more force than the weight of the rocket itself. So how these work, they burn a combustion reaction of liquid hydrogen and liquid oxygen. Now, that in and of itself is a massive engineering challenge because liquid hydrogen is the second coldest liquid on Earth. The coldest liquid is liquid helium. So it's very difficult for hydrogen atoms to bond together. This is a very non-scientific term, but you'll get it. Hydrogen atoms aren't very sticky, okay? Nitrogen atoms, like we can make liquid nitrogen, that isn't a big deal, okay? Because nitrogen atoms are bigger and they're a little bit more sticky. Hydrogen atoms are very small. So to get liquid hydrogen is extremely difficult because it has to be kept under such extremely cold conditions. So in this combustion chamber of these rocket engines, here's the problem. From an engineering perspective, you have to take liquid hydrogen, second coldest liquid on Earth, combine that with liquid oxygen, which is still pretty cold, but not as cold as liquid oxygen. So your pumps have to handle these extremely cold temperatures, which is, if you've ever dealt with cold metal, metal behaves very differently when it gets very cold. Number one, it contracts, okay, and it becomes very, very brittle. So you have to have, and it isn't just, oh, we'll just let it mix together. Okay, you all saw what happened yesterday with the hydrogen balloon. Oh, okay, that was kind of a cool thing, right? So basically, this is a huge number of hydrogen balloons going off all at once. Okay, that's basically what happened. So the problem is that you all saw that explosion. There was a very exothermic reaction. Okay, it expands rapidly. So the engineering problem is that the exhaust coming out of those rocket engines is hot enough to not only like melt iron, it will boil iron. So if you've all seen boiling water, imagine boiling iron. Okay? So within the same system, you have to handle two extremely cold liquids and the pumps that handle them. And then on the other side of it, you have to design materials that handle those extremely high temperatures. So all within the same system, this is why rocket science is so tough in terms of the engines, because you have to have extremely cold liquids, handle those, have them combust, they explode in a controlled, hopefully controlled circumstance, and then you have exhaust gases hot enough to boil iron. Therein lies the challenge. Not to mention the whole navigation thing, keeping you upright, all of that. So this is why, getting stuff into space is extremely difficult. So the other thing that happens from a mathematical standpoint is that, and we'll talk more about this later, when you talk about rocket engines and how they work mathematically, the force that you generate is a function of two things. The rate at which the fuel is burned multiplied by the velocity of the escaping gas. Okay? So we'll study more of this later. Don't worry about it for now. So basically, if you want a big force, you have to consume a lot of fuel per unit of time. Those engines typically consume about 3,000 kilograms of fuel per second. 3,000 kilograms is like about 2 big cars, okay? So for every second that goes by, you're burning about 3,000 kilograms per second. Also, if you want a big force, you want those gases to escape at a large velocity. So here's the nuts and bolts of rocket engine design. You want a big force, you have to consume a lot of fuel in a short amount of time, and you have to have that gas escaping rapidly. So that escaping velocity is usually about 3,000 meters per second. So, but again, it's a catch-22. You go, oh, well, we need more force. We'll design bigger rockets. Cool. You design a bigger rocket. Well, if you design to build a bigger rocket engine, guess what? Bigger rocket engines weigh more. So now you have more weight that you have to get up in the air. Guess what? Bigger rocket engines require more fuel. Oh, now we have to carry more fuel because we have to feed the rocket engine itself. So it becomes this nasty catch-22. It's like, okay, we'll build bigger rockets, those consume more fuel. Now, assuming that we get the rocket up in the air, which we obviously did, so an interesting thing happens. So if you look at the idea that force applied plus force opposing equals force net, okay? So the rocket engines are pretty much a constant force, okay? You can vary a little bit, but pretty much that's the same. So as the rocket itself goes up in the air, what do you think happens to the mass of the rocket?
It decreases.
It decreases. Why?
The fuel goes down.
You're consuming fuel. Okay, just like if you fill up your car with gas, as you drive your car, what happens to the weight of your car? Oh, it goes down because you're burning fuel. So imagine that you're burning like 3,000 kilograms of fuel per second. So what happens is that this opposing force becomes less. Okay? Now, this is what you want to think through. So as your opposing force becomes less, what happens to, and assuming that your applied force remains constant, if your opposing force becomes less and your applied force is constant, what's going to happen to your net force? So I'm going to have a bigger and bigger net force because I'm having the same applied force, but my opposing force is becoming less because I have less mass. Now, here's the interesting thing that happens. Then, your acceleration is force net divided by mass. So look what happens. As the rocket goes up, what happens to your net force? It's getting bigger. But what happens to the value of the mass?
Smaller.
It becomes smaller. Okay? So you have a bigger net force acting on a smaller mass. So what's going to happen to your acceleration? It's going to increase. So your acceleration, stay with me here, accelerates as a function of time. Because you're having a bigger net force operating on a smaller mass, so you have less stuff to accelerate. So what happens if you look at an acceleration versus time graph for a rocket? It goes something like this. So your acceleration actually becomes larger as a function of time because as you burn more and more fuel, you have less stuff to accelerate. Your acceleration actually becomes greater. Okay, so let's go back. Yes?
What would the distance time graph look like? Is that just exponentially?
Oh, yeah. There'd be like an exponential.
Okay, yeah. So
If that makes sense.
Yeah.
So,
Exponentially.
Universe among the stars. Launching a rocket into space is one of humankind's crowning achievements. Although they come in many different shapes and sizes, all rockets are propelled by engines that produce thrust. The rockets that launch into space are made up of 4 major systems based on function. The structural system makes up the frame that holds a rocket together.
kind of important.
Consists of the cylindrical body, nose cone, and fins. Next, the propulsion system takes up the most amount of space and includes the rocket engine, fuel, and oxidizer. The payload system depends on each mission and consists of anything a rocket is carrying into space, like a spacecraft, satellite, or human being. Lastly, the guidance system is made up of radars
Kind of
and
important.
computers that provide stability for the rocket and control maneuvers in flight. In order to launch into space, all 4 of these rocket systems must work together to overcome the force of gravity. The launch begins when the rocket's propulsion system starts to generate a massive amount of thrust. Thrust is the force produced by burning fuel as exhaust gases escape through the engine. Once the rocket generates more thrust than its own weight, it lifts into the air to begin its powered ascent. During this phase of the flight, the weight of the rocket will constantly change as fuel continues to burn off. As a result, Most space-bound rockets use a technique called staging to reduce dead weight and increase efficiency. The method involves breaking up a large rocket into 2 or 3 smaller rockets that fall away at different stages of the launch. As the rocket continues into orbit, its sophisticated guidance system maintains balance and steers to keep the flight trajectory on track. At the correct altitude and speed, the upper stage engine cuts off, completing the rocket's journey from Earth's surface into orbit. Long before blasting into space, rockets were used here on Earth as early as the 13th century. The first known rockets were introduced by the Chinese in 1232 AD. These fire arrows were used to fight against invading armies and were made by attaching fireworks packed with gunpowder to long arrows. By the 16th century, the use of rockets for amusement had spread from Asia to Europe, where they gained popularity in elaborate firework displays at celebrations and festivities. During the following centuries, the work of scientists like Isaac Newton and his laws of motion began to greatly increase knowledge into the forces behind rocketry and how to control them. And by the end of the 18th century, military forces around the world began to apply these new scientific understandings to the battlefield, transforming the earlier crude rockets into powerful weapons of war. However, the true dawn of space rocketry began in the early 20th century, thanks to massive technological improvements in rocket science and aeronautics. By the 1950s, the stage was set for the modern space age, and development began on sophisticated launch vehicle systems like the Atlas rocket family, which launched America's first astronaut into orbit, the Titan rockets, which were behind the pivotal Gemini missions during the space race, and the Saturn rocket family, which includes the largest and most powerful rocket ever successfully launched, the mighty Saturn V. Standing as high as a 36-story building and weighing more than 3,000 tons, this behemoth was used to launch the Apollo missions to the moon.
We choose to go to the moon not because they are easy, but because they are hard.
Since the beginning of human history, adventurers have looked to the skies and dreamt of touching the stars. And today, innovations in rocketry are opening up possibilities to launch astronauts farther into space than ever before. Whether our sights are set on the moon, Mars, or beyond, the future of rocketry and space exploration is only just blasting off.
Okay. Yes, Eli.
I have a question. So when it like breaks apart, where does the stuff go that like breaks? Just like in
It
orbit?
basically re-enters back into our atmosphere and burns out.
Okay.
Wait, how do they land on Earth again? If they're just a tiny little thing.
Well, it depends on what you want to do. Most of them are just like if
They
you're
just go in
launching a
the ocean?
satellite, it's just a one-way trip.
Oh.
But if you're like going to the moon, that's why you have the capsule
Oh yeah.
with the heat shield that has to withstand the re-entry into our atmosphere. So it just depends on what it wants to do.
What if we stop using a satellite? Do we
Well,
just
then
leave
it just burns up on re-entry.
That's kind of crazy though. I didn't realize how like much of the rocket is just the what's it called?
Basically,
Like
it's
the engine, basically.
On
the
February
fuel?
29, 2020, YouTube and the world were significantly improved with the release of Flat Live's first ever video. The evolution of SpaceX
I have no
rockets.
idea how that got.
Seriously though, there have been a lot of developments both at SpaceX and on this channel since then. So
Why
I
is this
figured it's
playing
time
on
to
brand
update
new?
a portion of that original
He
video.
must have clicked on the side on accident because it's the next video.
I'm kind of invested in this one.
Can we watch this one too?
This is the evolution of SpaceX.
I want to
Do you like SpaceX?
I do, but that's not what I want
You
to
do?
watch. There's time and place.
3, 2, 1, 0. All
Oh yeah, didn't
I slid it.
Tesla at the same time?
Yeah.
I slid across the tennis court.
I swear. Let's try this one more time.
That's like half
They get the rocket.
Okay, so let me explain the different types of rocket fuels that you can have. So this was a space shuttle. Was the space shuttle even flying when you guys, in your lifetime?
I have no idea.
I don't think so.
It might have been retired before.
I was
it
born
staying.
18 years ago.
So, so here's your Saturn V rockets. So the Saturn V rockets, those all go off of liquid propellants. It might be kerosene, it might be liquid oxygen, it might be liquid hydrogen. Those are all propellants. The cool thing about those is that if you go to start them and there's a problem, you can shut them off, okay? So that's a good thing. But they're very expensive to build because you have to deal with such complex parts. So the space shuttle had two main components. It had your traditional rocket engines here on the space shuttle itself. And then this is something that Morella asked about, how did it get back? So the cool thing about the space shuttle, basically it was like an airplane. So it would launch into space and then everything else would get discarded and the shuttle itself would return and land back and we could reuse it. So that was the cool part about the space shuttle. So the space shuttle had two primary engine systems. It had your traditional fuel, one's liquid hydrogen and liquid oxygen. But on the outside of this, and that's what these engines are here, those are known as solid rocket fuel engines. So solid rocket fuel engines basically burn typically aluminum oxide. Aluminum oxide, when it burns, produces a very, very large amount of thermal energy. So the advantage of those is that they're cheap to build. Okay, you just have to have a whole bunch of aluminum oxide. There's no pumps or anything like that. So it's almost like a firecracker. The disadvantage of it is that if you ever light them, you can't shut them off. Okay, so there is no like, oh, let's just shut off the switch like on your car. Oh, we're done. Oh, we'll just shut off the switch. So that's the bad thing, is that solid rocket fuel boosters are relatively cheap to build, but there's not an off switch. So you better make sure that you're ready to go when you light them because there's no way to shut them off. So we'll run this for a little bit. So it's kind of cool because they're using like the voices of like the actual like launch command centers. So you notice that it's cool because you're seeing like your fuel levels are decreasing as it's going. So what's going to happen is that when these get emptied off, there's a solid rocket boosters at the bottom stage of that Apollo rocket. They don't need it anymore, so they jettison those, and that's what burns up in the atmosphere. And it's cool. They have like sound effects, like the spaceship like rattling a little bit. And they even show like transitioning into space because it's getting dark in the background.
For mode 1, Charlie. Mars, mode 1, Charlie. On Charlie.
Seconds into the flight. Discovery 22 miles in altitude, 23 miles downrange. Standing by for solid rocket booster separation.
This is Houston, you are go for
Okay, so what happens with the space shuttle, so these are those two solid rocket boosters on each side. Those are jettisoned within the Earth's atmosphere. Those were actually reusable as well. So what happens with those is they actually had parachutes that were built into them, so they would jettison, fall off, F equals ma, less mass, then we can accelerate more. So those would fall off, they'd parachute, they'd land in the Indian Ocean, in the Indian Ocean, they'd recover them, they could reuse them again. So that's what's going to happen with these. Now, the other ones, like those, like especially with the Apollo mission, those would actually be jettisoned when they were in outer space, and those would actually then burn up. Now, with the space shuttle, it still has this big external tank, so that one would actually get jettisoned out in space. So with that one, what they would do is that when this thing gets jettisoned off the space shuttle, they actually had a valve that would open so it would begin to tumble. So they would want it to tumble when it re-entered the Earth's atmosphere. They didn't, that way they knew it would burn up, because the concern is if it wasn't tumbling, it would act like if you've ever thrown like a smooth stone on a body of water and it just skips, okay? That's the concern. So this has a valve, it would open up, it would begin to tumble, and then that way when it hit the Earth's atmosphere, it would burn up, as opposed to hitting the atmosphere, skipping, and then going out into space and potentially colliding with other satellites that are orbiting the Earth. So there goes the bottom stage of that Apollo rocket. There goes your side boosters there.
You're looking good. You're not clear yet.
Okay, y'all get the idea.
Wait, so how long does it take to get to the space?
Usually about 8 minutes.
Oh, wow. Wow.
Doesn't take. So
For some reason, I thought it was like really short.
hold on.
Like 2, 3 minutes.
8 minutes is short. She's thinking like the movies where you act like 5 seconds.
Yeah, like it's like 2 or 3 minutes and you're in space. To be fair, I've never been on an airplane before, so I don't.
You've never been minutes.
No, so I don't like know. There's nothing to compare it to.
We're talking about minutes. A full.
No, have you? I mean, I have like when I was 1, but how am I supposed to remember that? I've never really been on an airplane like now.
A full 24-hour drive in a car could only take like 2 to 3 hours of time.
Okay, so to give you a relative
24 hours.
scale of what it means to be
Yeah,
in
that's how long it
space,
takes to get to China.
and we'll talk more about this later. But basically what happens if you want to be in orbit, imagine that you're standing on top of a mountain, okay, and you throw a rock or a golf ball, okay? So if I throw that rocket, or if I throw this, it's going to travel a certain distance before it lands. The faster I throw it, the further it's going to go before it lands. So imagine that I could throw, which would be cool, imagine that I could stand on top of a mountain and throw this ball fast enough so that the Earth would just continuously curve out from underneath that ball if I threw it fast enough, which would be the ultimate physics demo. It's like, okay, class, let's go outside. I want to throw this thing really, really fast, and it would take about an hour and a half to come back. So this would be the ultimate orbital demo. So it's like, okay, beginning of class, you know, you all get in here at 11:30, we're going to go out and we're going to throw this tennis ball. We're going to come back in, lecture for about an hour and a half. We're going to go back an hour and a half later. I'll put my hand up, boom, catch it. There we go. So on a relative scale, when we talk about our atmosphere and something being in space, if this was the size of the Earth, our atmosphere is about a half an inch. Okay? That's it. So the only thing to be in orbit or in space, we just have to get above our atmosphere so that that atmospheric drag colliding with our atmosphere doesn't happen. So that's why it doesn't take very long to get into orbit, because you just have to get above our atmosphere. If this is the size of the Earth, it'll only be about 1/4 of an inch thick. Okay? So that's an important 1/4 of an inch, because without it we wouldn't be here talking. All right. So what we're going to do, how this lab is going to play out. I've got a program. Hold on. I got to switch computers.
It stops stress. It helps with stress. It really does. It helps. Yummy. I feel so relaxed.
No, I told my wife I was really stressed out, and so she got me that.
Give me 1 second. I got to
You know, it's just aromatherapy.
So now all my problems are fixed, obviously. I'm back in the
Look at the snowflake.
Thank you, Grace.
Where? It's right in front of you.
Oh. Is that what I smell?
Is that the aromatherapy stuff? Which one?
Wait, Gracie, how'd you get that stress relief a
Oh, I like that one.
I already told them.
I want some more.
Mr. Bergkamp.
What?
So the aluminum oxide.
Hi, Maggie. We miss
Is
you.
that the stuff that we like lit on fire in Chem 1 and it was like crazy?
Thermite, basically.
That would be good for the camera. Wow.
What? Oh my god. Will you just shut up?
Why is it Maggie?
Give me 1 second.
Merle, fix the camera.
Shut your mouth. You messed it up.
She probably have,
Maggie, where are you?
I miss you, Maggie.
Mallory's head. I'm okay for it.
I'm kidding. It's a joke. Are you gonna do an E? You can say it, Maggie. Do an E.
Is this yours?
Yes, that's mine.
Ooh, I like your shorts.
Are you gonna ask first?
You bought them for her.
Why, Grace, look how mad at you for texting her.
You're being very demanding.
I'm a physicist. Dude, every guy, he's like, can you send me the answers? Yes.
He's like, he sent me this too. Oh, and this.
I need to check.
I didn't sign.
Here's what's going to happen between today and Monday.
Everybody's hello.
Okay. So this is a program that's loaded on the laptops. It's called Interactive Physics 2000. So what this is going to simulate is this whole idea of, in this case, landing something on the moon. So you're going to try and land the lunar excursion module on the moon. So the program itself isn't horribly complicated. You hit launch, and you can control the value of the main thruster, which is that main vertical engine. So you can adjust that, and it might go off the screen. It'll come back eventually. Maybe. There it goes.
Oh, yeah.
And then you can make it go left or right. Stop it. Okay. Thank you. It's like, what are you doing after school? I'm working on my lesson plan. Okay. So let me explain how I've set up this program. So if you click down here in this bottom corner, you can like make it. You can replay the landing sequence. Okay. So what I've got going. So for example, here's what this thing is keeping track of. This is AX, so that's your acceleration in the horizontal direction. This is VX, your velocity in the horizontal direction. This is AY, which is your vertical acceleration. This is your VY, and then this is the value of the main thruster, which is the value coming out of this engine. So how I've set up the parameters of this program, and I've got all this on the paper. So you're assuming that the acceleration on the moon is negative 1.67 meters per second squared. The mass of the ship is 5,000 kilograms. To make this simple, we're going to assume that the mass of the ship remains constant. Okay? Yes, technically it's burning fuel. Technically the mass is decreasing. but that's going to get real ugly based upon your fuel consumptions and things like that. So we're just going to assume that the mass of the ship is going to remain constant. So if you're going to land it on the pad, how the program is set up, everything going down and to the left is defined as a negative value, whether that's displacement, force, acceleration, anything. Anything left and down is negative. Anything up and right is positive. So if you look at this value of the main thruster, that's 7,400 newtons. So that's the vertical force coming out of the engine. Now let's just think this through. I have a value, this is my force applied. So the value of your main thruster, listen to me, the value of your main thruster is your applied force, okay? So I get a 7,400 Newton value of my main thruster, 7,400. I have a negative acceleration in the vertical direction. So think this through. Since I have a positive applied force, but I still have a negative acceleration, is the ship weighing more or less than 7,400 newtons? More or less than 7,400? More. Weighs more, right? Now, gravity is going to be pulling this ship down. So what this means, if I just look at this, I got to figure, here's the value of my main thruster. I still have a negative acceleration. That means that whatever that ship weighs has to be more than 7,400 newtons. So, and the same rules apply. I've got a negative acceleration and I've got a negative velocity. So I'm right here on this velocity time graph. So I'm right here on this velocity time graph. I have a negative acceleration and I have a negative velocity. Am I speeding up or slowing down?
Speeding up.
Speeding up. Why?
Same sign.
Have the same sign. So the same things apply, right? Oh, I have a negative acceleration, negative velocity. I'm speeding up. So what this tells me is that I'm speeding up going down, okay? Which might not end so well for the ship. So then, but if I change it a little bit, oh, come back here. And I come over here, okay, like at this point. Whoa, that got crazy. Okay, now let's look at this one. So at this point, I got a 9,400 Newton force. So now my applied force is 9,400, but now I have a positive acceleration. So this tells me that the value of the main thruster is bigger than the weight of the ship. So when you're flying this, and so what's going to happen on Monday, I'm going to give you all the lab. You're going to have the first 2 pages of the lab done. Then I'm going to turn you loose on the computer, and you're actually going to try and land the ship. Okay? So when you're actually flying this thing, watch what happens to the value of that main thruster and that acceleration. If you can watch these 2 values, that will tell you if you're speeding up or if you're slowing down. That'll be important when you actually try and land that ship on Monday. So let me hand this out, so stop that. Okay. So here's what's going to happen on Monday. So there's 2 pages of Assembly Flab, so what you need to have done by the time you come in on Monday is the front page, front and back. So basically, just like NASA isn't going to go, you know, you can't walk up to NASA and go, hey, I'd like to fly one of your spaceships. Okay, here you go. Look, I'm not going to turn you loose on this program until you prove to me that you understand this concept of net forces and Newton's laws of motion. So up here at the front, I lay out the parameters. The gravitational acceleration on the moon is negative 1.67 meters per second squared. The mass of the limb is 5,000 kilograms. Anything, displacement, velocity, acceleration forces, up or right is positive, down, left, negative. Okay, so that's how I set up the parameters of the ship. You have to land it with a velocity less than -1. So basically, you built this ship for efficiency, for lightweight. So basically, we didn't land this thing where you can crash it in and it would still survive. So that's why you have to land with a velocity less than -1, like -0.9, -0.8, something like that. So pay attention to the numbers, pay attention on a bunch of these. I'm going to ask you to draw a free body diagram. So like down there on number 6, you're going to draw a free body diagram, okay, showing all the forces acting on it. You've got another one to draw over here on the top on page 9. And again, these are just sketches. You don't have to draw them to scale. These are just sketches. So what's going to happen on Monday, you all walk in, you're going to come up and say, hey, Mr. Burkamp, I think I've got these right. I'm going to look through them. If you need to make any corrections, you'll make any corrections. Once all the corrections are done, then you can grab a laptop, then you can actually try to land the limb. So that's what you've got to Monday, is to get done with page 1 and 2. Okay? Got it? Good? Okay, so Merrill will stop you on there.